All right, this isn't a physics problem, but it's an interesting problem. A couple of people have asked me to explain the rule of 72. So that's what we're going to do. We're going to explain the rule of 72. And what the rule of 72 is, it gives you the time to double your amount of money. And it's equal to 72 divided by the interest in percent, and the result is in years. So as an example, let's say you're making an investment and it's collecting at an interest rate. We're going to stick with a yearly rate. You can do compounding more often, daily, monthly, whatever. But we're just going to use the simpler case of yearly interest compounding. And it won't make that much difference in the end anyhow. So if the money is accruing 6% interest per year, and you want to find out how many years will it take to double your amount of money, it'll be 72 divided by 6, or 12 years. If it was 3%, it would be 24 years. One of the things we'll use in this is, I'm going to use the abbreviation capital LOG for the natural log. So some people like to write it ln. Some people like to write it log, and that's the natural log. Some people also like to write it as log to the base e. So we're going to use this for the natural log. Now to start this off, we'll work out an expression for how the money grows compounding yearly. So let's say you start out with an amount of money P. What will you wind up with after a year if it's collecting at a particular rate? And what we're going to use R for the rate. And if 6% in terms of rate is 0.06. As an example. The reason for using rate this way instead of in terms of percent is to avoid carrying around a bunch of 100s. So we're going to say rate instead of interest in percent. It's rate. So you start out with the amount of money P, and after 1 year, you'll have the amount of P, and we're using R for the rate, and then we'll compound that with the amount RP. So after 1 year, this is what we wind up with. The next year, we start out with the amount we wound up with at the end of our first year, and now we're going to have added to that the rate times that amount again. So if we work this out, let me just indicate that this is equal to 1 plus R. So if we work this out, we can factor out the P, and we would have 1 plus R from here, and this is giving us another R, so we're going to have 1 plus 2R. And this times that will give us an R squared. So we have R squared. So we have 4 quantities here. We have 3 here because we combine this R with that R. And of course that is equal to P times 1 plus R squared. Now we do it again. We keep doing this. So this is what we wind up with after 2 years. So third year, we start out again with this amount. And then we're going to have our rate times that same amount. So we can factor out the P again. and we can combine terms. We're going to have the 1. We have 2r here, and we're going to get an r there, so that's going to give us a plus 3r. We have an r squared here. This r times that r will give us a 2r squared, so we get a 3r squared plus this r squared. That's in here. Then we're going to have the r times this r squared, and that gives us r cubed. And that is equal to P, the amount of money we started out with in the very beginning, times 1 plus r to the 3rd power. And just as a little bit of a kind of a sidebar, we can keep going on this. There's something called Pascal's triangle. We're going to take a little detour here. And the way you draw the triangle, you start out with 1, 1, 1. Then you do 1, 2, 1. This 2 comes by from the sum of those two 1s, and then you wind up with 1, 3, 3, 1. Then you wind up with 1, 4, 6, 4, 1. So if we had done this for another year, we would have wound up with an expression like this with these coefficients. So this would have been the 1. We would have had this 4r plus this r squared, r cubed, r fourth, and that would have been equal to 1 plus r to the 4th. So Pascal's triangle is a neat way to be able to write down the coefficient. And we could keep going here. We would have 1 and 5 and then 10 and then 10 and then 5 and then 1, and that would be 1 plus r to the 4th. All right, so that's a minor detour. But what you can see happening if you just kept going and going and going, what would you conclude? So this is the 3rd year, these two. So if you went to some time, it would be P times 1 plus R to that number of years. We're going to let T equal the number of years. So that's what we would find. So that's how the money grows. So now the question is, you want to find the time so that this amount doubles. So in other words, you're asking to solve this equation. 2p is equal to p times 1 plus r, number of years, t, and we want to find out what that t is. And that's where the logarithm will come in. So the p's cancel out. So we're left with 2 is equal to 1 plus r to the t. And we want to solve for t. So what we do is we take the log of both sides. So we're going to wind up with the log of 2 over here. On the other side, we'll wind up with the log of this expression, but the log of an expression like this times an exponent is equal to the exponent times the log of what's inside. So all I did going from here to here is I took the log of both sides. And again, the rate that we're showing here, the R, that's not in percent. And again, that's just because I didn't want to carry a bunch of factors of 100 all over the place. So we can solve this for t. The time that it takes to double your money is equal to the log of 2 divided by the log of 1 plus r. This is exact. Now we want to come up with an approximation for this. And the approximation will come about by looking at what we can do with the log of 1 plus r. So we can look at that and expand that out in a series, and if we do that, we get r minus r squared over 2 plus r cubed over 3 minus plus all the way down the line. So this is a series. It's called the, it goes by different names, Newton-Mercator series. In case you want to take a look at that Newton-Mercator series. It's interesting if r is equal to 1, because then you get 1 minus 1/2 plus 1/3 minus 1/4 and so on. So what we can do by using this is say that we can come up with an approximation. We'll just take the first term. Take the first term, r. So we're going to have the log of 2 divided by r. Now we're almost there. The log of 2, you can use your calculator. You can, the natural log of 2, you can look it up. We'll just put down a couple digits. 0.3, I think. So that's the log of 2. I want to make sure we carry the approximation sign. So in terms of percent now, if you would want to do this in terms of percent to get to the rule of 72, we would think of this as 69.3, and now we're going to express the interest in terms of percent. That's not 72. So you might want to just say, well, that's close to 70. So that's another approximation you could make. But I guess somebody along the line decided it's easier to divide the various interests that you'll come across if this numerator is 72. So you can sort of fudge things and say that the time that it takes to double the amount of money is 72 divided by the interest in percent. And that's what we wanted to show. Now, how accurate is that? Actually, it's pretty accurate. And to show how accurate that is, we're going to go back to the interest. And we want to introduce another variable. We'll call it Q. So whatever this numerator is in terms of rate, we're going to call that Q then. So in this case, Q right here is equal to this, but we're going to just look at a general case now. So we have the approximate. So this is our exact formula. And our approximate one is what we're going to call this Q over R, approximate. So what we could look at to find out what kind of accuracy we get with this very simple development, we could take the exact amount, the log of 2, over the log of 1 plus r. And look at the difference if we had the approximate case. And again, we introduced this parameter so we can see whether is 0.69 better than 0.70, better than 0.72, which corresponds to 69, 70, or 72 if you do things in terms of percent. So again, that's what that parameter Q is. So we would compare that to the exact value. And if you want to think of this as an error, and think of it as an error in terms of percent, now that's not interest percent, this is error percent. It would be equal to this multiplied by 100%. So we have two variables here now that we can look at. One is the R, and the other is the Q. So what that kind of suggests is it might be a good idea to take a look at a three-dimensional plot. This would be, say, error, and this might be the R, and this might be the Q, or the other way around. So we would do a three-dimensional plot to see what the error looks like. And I did that over here. So if we come over here, here's the error expression. I should have a percent here. So the error in percent is what I showed you over there. Here's that parameter Q, and there's our R. So I made a three-dimensional plot. And what I did in doing this three-dimensional plot, I put in a zero reference plane. The zero reference plane is where the error is 0. So if you lie on the zero reference plane, there's no error in the result. And this is the parameter Q. The little arrow here is pointing out to the rule value, the nominal one, of Q equal 0.72, or in terms of percent, that's 72 right there. And the error, this expression here, I've plotted here as this plane. So you can see you have this horizontal plane, the zero reference plane, and the error plane, which is a function of the rule value and the interest rate, the rule value being the value of Q. And you can see they intercept. And as an example here, I put a little X right there. So at 72, that corresponds to 8%. So if you could look from this graph from the other side and see where it's falling, it would be lined up right here with 0.8 or 8%. So it's very good for Q equal to, we'll do it in terms as if we had the interest in percent, so we'll say 72. Well, let's do it the other way. We'll do it 0.72, and that corresponds to 72 if we're speaking in terms of percent. And the interest rate, that corresponds to 0.08, put a 0 here, or 8%. So it's really good around that value. But you can see it's pretty good no matter what your percent is. Here's the percent running across here. Percent and rate, I show both of them. The difference is a factor of 100. And you can see the error is just in few percent in most places for different values of Q. So it looks like picking Q as 72 when you're doing it in terms of percent is good. So the time to double your money at a interest rate R, or in terms of percent, would be 72 approximately. 72 over the interest expressed in terms of percent. And that's what we had, and we tried to use this three-dimensional plot to justify the 72 compared to the other values. So the whole process involves an approximation. You wind up with the natural log of 2, which is 0.693. And then you float around that number a little bit. And the business people like 72, because it's easy to divide numbers into 72 instead of 0.693. And you can see how things work out with that three-dimensional plot. So if you want to figure out how long it takes to double your money, take the number 72 and divide it by the interest in percent, and that'll be roughly the time it takes to double your money.